everybody, welcome back to chemistry, and today what I want to talk about is how do you determine the electron configuration of an atom? In other words, how do you figure out for a particular atom into what orbitals the electrons go into? So let me just give you a quick example of a problem that you might see in the future. And so what may happen is that you may be asked to give the configuration for an atom of the element scandium. And so the symbol for scandium is Sc. And so you can look up the atomic number of scandium, and what you'll see is that there are 21 electrons. And then you'll be asked what the electron configuration of scandium is. And so what you'll have to figure out is this, that you'll have to somehow figure out that there are going to be, first off, 2 electrons in the 1s sublevel of scandium, and then 2 electrons in 2s, 6 electrons in 2p, and then 2 electrons in 3s, 6 electrons in 3p, and then you have 2 electrons in 4s, and then finally we have one more electron. It's in the 3d sublevel, and so it's 3d1. So that is the correct electron configuration for a scandium, and so I need to teach you how to figure that out. And so in order to figure that out, what I'm going to do is I want to point out something, if I can increase the slide here. So here I have a description of all the sublevels that an atom can have, and what you can see is they're charted in terms of their energy. So I want you to notice that the y-axis here is an energy axis. And so the lowest energy sublevel is the 1s sublevel. And then the next one up in energy, has a little bit more energy than the 1s, is the 2s sublevel. And then here next you have the 2p sublevel, and then the 3s sublevel, 3p sublevel, and so on. And so if I can reduce the slide, what you have to figure out is what the order of sublevels is in terms of their energy. And so you can sort of memorize that chart, but there's probably an easier way to do it. The way you figure out what the order of sublevels are in terms of their energy is using something called the diagonal rule. And so let me show you how to set this up. And so in the first energy level, you might recall there is only an s sublevel. So let's write that here like that. Now, is there a p sublevel in the first energy level, or a d or an f? And the answer is no. The first energy level only has the s sublevel. When you get into the second energy level, there is an s sublevel. I'm going to write that underneath 1s, but also there is a p sublevel in the second energy level, so there's a 2p. And question is this, is there a 2d sublevel? And the answer is no. You may recall that you only start seeing d sublevels when you get into the third energy level, and so that's it for the second energy level. And now there is the third energy level, which is 3s, 3p. There is a d sublevel in the third energy level, but there's no f sublevel. What's next is the fourth energy level, 4s, 4p, 4d, 4f, and then you get into the fifth energy level. So it's 5s, 5p, 5d, 5f. And so you might be wondering if there's another sublevel in the fifth energy level that is beyond the f sublevel. Well, it depends on the chemist you talk to, but in this class, to sort of simplify things in writing electron configurations, we say that the highest sublevel that you can have for any energy level is the f sublevel, and that seems to work out pretty well. So in the fifth energy level, you only go out to 5f, and that's it. And same thing with the sixth energy level, write them like this, and you only go out to the f sublevel, and that's it. And same thing with the seventh energy level, and I think that should be enough sublevels. Okay, so now what you're going to do is to figure out the order of sublevels that are filled by electrons. You're going to draw diagonal lines to this chart. So I'm going to start the arrow up here. It goes diagonally through 1s, and so this is the first diagonal line. So the second diagonal line only goes through 2s like this. The third diagonal line goes through 2p and then 3s. Fourth diagonal line, 3p, then 4s. Fifth diagonal line, 3d, 4p, 5s. Sixth diagonal line, 4d, 5p, 6x. Seventh diagonal line, 4f, 5d, 6p, 7s. And then you can do the eighth one, and that would go through here, 8s. That's probably enough. That's enough diagonal lines. So using this chart, let's go ahead and figure out the order of the sublevels that are being filled by electrons. And so what we're going to do is we're going to list them out here, and the first sublevel that is filled will have the lowest energy, and then as we figure out orders that are filled next, they will have greater and greater energy. So you have the first diagonal line goes through 1s. So the first sublevel that is filled is 1s. And I'm going to put a little comma here like that. After 1s, you go to the second diagonal line and you see the 2s is filled. So it's 2s like this. And then you have to go to the third diagonal line and you see it's 2p3s. And then after 3s, we have to go to the fourth diagonal line, 3p4s. And then now, looks like we have to go to the fifth diagonal line, 3d, 4p, 5s. So 3d, 4p, 5s. And so you could continue figuring out the next sublevels that are going to be filled in terms of their energy. So this is just to remind you here, I'm drawing an arrow like this, that these sublevels have increasing energy. Okay, so now I think we're ready to go to figure out what the electron configurations are of certain kinds of atoms of the different elements in the periodic table. So what I'm going to do is take a moment to make a chart here and I'll get back with you. Okay, so now what I want to do is figure out and write down the electron configuration of all the elements in the first and second period, which would include all those from atomic number 1 to atomic number 10, and then we'll also do atomic number 23 as well. So before I begin this process, I want to point out here, what I've done is I've listed the order in which these sublevels are filled. So the first sublevels that would be filled by electrons will be the ones with the lowest energy here, which is the 1s sublevel. Once that is full, then we go on the 2s, the 2p, and so on. Okay, so let's go ahead and try to figure out the electron configuration for the element that is atomic number 1. I think you all know at this point that element is hydrogen, so its symbol is H. So the first thing I'm going to do is write out something called the orbital notation for hydrogen's electron configuration. So this is what you do. So you first ask yourself this question: into which sublevel does this electron go? Does it go to any sublevel or does it go to a particular sublevel? Well, the sublevel it goes to is the one with the lowest energy that is unoccupied. And so right now, we have a 1s sublevel that's unoccupied, that has the lowest energy, so that's where that electron will go. And so the way we indicate that is we draw a single line for an orbital. And you might remember that any s sublevel only has one orbital, and that's why we're drawing one line. So again, the line is the orbital. So I'm going to indicate that this is a 1s orbital because it's in the 1s sublevel. And then what I want to do is indicate the electron in this orbital. And so the way we indicate electron is with an arrow. In this case, it'll be pointing up, which is fine. And so that completes the orbital notation for the hydrogen atom. Now, let's go ahead and figure out its electron configuration notation. It's another form of writing out the electron configuration of an atom. And so what you do is you write out the sublevel, which is 1s, and then with a superscript, you indicate the number of electrons in that sublevel. And so there's going to be one electron here. Okay, so we're done with hydrogen. So let's move on to helium. So helium is atomic number 2. And the first sublevel that you might expect helium's 2 electrons to go into is the 1s sublevel. So we're going to write 1s like this. So the first electron goes in like that, but we have a second electron. So the question is this: does it go into the 2s sublevel, or does it fill up the 1s sublevel? Well, you might remember every orbital, which is indicated by a single line, can have 2 electrons. So we can fit in a second electron here. But here's the thing, and I need to sort of show you this here, that when we put an electron in here, if there is an electron already there, somehow we have to indicate that its electron spin is opposite of the first electron spin. So electron spin, sort of like the Earth rotates on its axis. Electrons are thought to rotate on their axis. That's how we think about it. And so here, this first electron, we can say it's spinning clockwise, and so we use an upward arrow. So here, the second electron can only occupy this orbital if it's spinning in the opposite direction, say counterclockwise. To indicate that this electron is spinning counterclockwise, then we draw the arrow pointing down like that. Okay, now for the electron configuration notation, we write 1s, and this time we have 2 electrons in this sublevel, so it's 1s2. Okay, let's move on to atomic number 3, which is lithium. So lithium, its symbol is Li, 3 electrons. So we have here the 1s sublevel is filled with the first 2. So where does the next electron go? So can we stick it in this orbital? And the answer is no. Orbitals can only have 2 electrons. So this 1s sublevel orbital is filled. We have to go to the next lower energy orbital, which is a 2s orbital. So we draw a line like this, and this is the single orbital in the 2s sublevel. This makes sense again because all s sublevels have only 1 orbital, so we had to draw one line. So this is 2s, and then we put the electron like that. Now, what's the electron configuration notation for lithium? It's going to be 1s2, 2s1. Okay, now I'm just going to take a digression for just a second before I go through 4 and the rest by pointing out another way you can write out orbital notation, which you'll often see, for example, in your textbook and other places. So let's look at hydrogen again really quick. You can see that we have written out that 1 electron is in the single 1s orbital. Another way you can write the 1s orbital is like this. Instead of using a line, you can write it as a box, and then you write 1s here, and then you draw the arrow like that. So what would be helium's notation? Well, it would be a box, 1s, and then an arrow pointing up, and an arrow pointing down, and then finally here, 1s, and then we have another box for the 2s orbital like that, and then here 2 arrows like that in the 1s orbital, which is now a box, 1 arrow in the 2s orbital box. Okay, so you can write it like that just to keep that in mind, but here, just to keep things a little bit clearer, I'm just not going to write this out, this notation anymore. We're just going to stick with the original notation where we have orbitals as lines, and that goes a little faster. Okay, so let's go ahead and figure out beryllium's electron configuration. So here, beryllium is atomic number 4, and so we have 4 electrons. First 2 go in the 1s, next 2 go in the 2s like this. This will be pointing in the opposite direction because it's spinning in the opposite direction, and its configuration is 1s2, 2s2. Okay, let's do boron. Boron has 5 electrons, so the 1s is filled with 2 electrons. The 2s is filled with 2 electrons. Now it gets a little bit tricky. We have to figure out where the 5th electron goes. So what is the next sublevel that is filled? It looks like it's the 2p sublevel. So here's the trick. For the 1s and the 2s sublevels, they only have 1 orbital because they are s sublevels. But now we're going to put electrons in the 2p sublevel. All p sublevels, no matter whether they're in the second energy level or the third or fourth, whatever, they have 3 orbitals. And so we must write out 3 lines like that. You've got to do that to indicate that you're in a p sublevel. It has 3 orbitals. So this is 2p. This 2p indicates for each of these orbitals that each of them is a 2p orbital. One oriented on the x-axis, one oriented on the y-axis, and one oriented on the z-axis. Where does that 5th electron go? We can put it right there. That's fine. And then its configuration is 1s2, 2s2, 2p1. Okay. Now we get to atomic number 6, which is carbon. And so let's go ahead and try to write out its configuration. So we have 1s, 2s, and then 3 2p orbitals. 2 electrons in 1s, 2 electrons in 2s, and then we have to figure out where the 2 electrons go in the 2p orbital. So you might imagine the first one, the 5th one goes like that. So the question is this: does the 6th one pair up this first one here, but just with an opposite spin? Or maybe does it go to another orbital? Well, there's another rule you have to remember. So let me just kind of bring up this slide really quick. Okay, if you can increase the slide. So here I just want to point out to you that we've already done the 1s sublevel here. We've already done the 2s sublevel, and now we're looking at the 2p sublevel. And you can see there are 3 orbitals here. What I want you to notice is this diagram is on an energy axis here. This is E for E. Well, there we go. E for energy. And I want you to know that the 3 orbitals of the 2p sublevel have exactly the same energy. Okay? And so you can see that also applies, say, if you were looking at the 3p sublevel. Those orbitals have the same energy. If you're looking at the 3d sublevel, here in the d sublevel we have 5 orbitals, and they have all the same energy. So if I can reduce the slide. So here's the rule. If you are adding electrons to a sublevel with more than 1 orbital, and these orbitals have exactly the same energy, you have to put 1 in each orbital before you put 2 in one orbital. So it would be wrong to put the next one there pairing up with this one. Again, here the orbitals have the same energy. We put 1 electron in each orbital before we put 2 in one orbital. So the next electron goes like that. So that is correct. And so its configuration is 1s2, 2s2, 2p2. Okay, next we do nitrogen, which is atomic number 7. So here we go 1s, 2s. I'm running out the 3 2p orbitals. 2 electrons in 1s, 2 electrons in 2s, 1 electron in each of these 2p orbitals. And so this is 1s2, 2s2, 2p3. Okay, what we're going to do now is we're going to do oxygen. What does that look like? So it's 1s, 2s, 2p. Looks like this. 1 there. Next one goes here. Next one goes here. So now what you can see is that we have 1 electron in these orbitals of equal energy. So we can now put in a second electron in one of these orbitals. And so I'm going to put the electron like this, spinning in the opposite direction. So this is 1s2, 2s2, 2p4. Okay, so what I'm going to do is I'm going to fill out 9 and 10, and then I'll get back with you. Okay, so I have written out the configurations for fluorine and neon. I suggest that you try those on your own and see what you get. I'm going to do one more configuration, that for atomic number 23, which is vanadium. So let me go ahead and do that really fast. So this is vanadium. So this has 23 electrons, so it's got a lot of electrons. So I'm probably going to need a little bit more room here. So give some space here. And so the 1s is filled, the 2s is filled, and the 2p is filled. So that is 10 electrons right there. but we have, what, 13 more to go? Okay, so what's next? Next is 3s and 3p. So 3s will take 2, and then the next is 3p. So this is 18 electrons. Well, we got 5 more to go. Okay, so what's next? 4s. It's an s sublevel, should only have 1 orbital. So this is 2 electrons. Now we're up to 20. So now we have 3 more. What do? After we fill up the 4s, we're now in the 3d. We're at a d sublevel. We have to indicate there are 5 orbitals in a d sublevel. So even though this is a 3rd energy level, it's still a d sublevel, and you have 5 orbitals, so I need 5 lines. So 1, 2, 3, 4, 5. So this is 3d. 1, 2, 3, like that. And the reason why we did that is because you may remember that if you're in a d sublevel, each of these 5 orbitals is equal energy. So we put 1 in each orbital before we put 2 electrons in 1 orbital. So that's fine. So let me write out an electron configuration notation. It is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. 2s2. Looks right to me. Okay. Thank you for listening. We'll see you next time.